Welcome to the video series on Atwoods machines. Atwoods machines covers material that is in Unit 5 with Newton's second law. So Newton's second law is going to help us out with this, especially the work that we did with double systems. So hopefully you've already watched the video on double systems, so you're already familiar with Newton's second law and how to use that. There are going to be actually 3 videos for Atwoods machines because there's 3 different types of setups that we can see for an Atwoods machine. First of all, we need to know what an Atwoods machine is, and it's kind of a little misleading because you hear machine and you think something a little bit more fancy than what it actually is. An Atwoods machine is simply a pulley system. So I have 2 Atwoods machines shown on the screen here. I've got the one on the left, which has the yellow boxes that are attached to a pulley that's probably suspended from, a ceiling or something like that. But the basic idea is that these 2 blocks are allowed to elevate up or down. And then also an Atwoods machine is what you see on the right with the pink boxes. So you've got the one block that's on the tabletop, and then you have the pulley that's attached to the end of the table, and you have the second mast that's hanging off the side. And you'd expect to see some kind of acceleration there, given the certain conditions and whatnot. So that's an Atwoods machine. Now we need to know before we're going into this that we are dealing with perfect strings and perfect pulleys. And what that means is a perfect string is a massless string. It has no mass. And a perfect pulley is a massless pulley, has no mass, and it's frictionless. And the rope is not going to slide through the pulley. Now, that might seem kind of ridiculous, but there's a reason why we have to say that. If in reality, the mass of the string and the mass of the pulley and the fact that the pulley probably has a little bit of friction on the axle that it's spinning on is going to affect the problem. And that opens up a whole host of complexities and lots of little nitty-gritty type things that you have to take into account, which we are not going to cover. So it's just important to know that anytime we're dealing with an Atwoods machine in this course, we are going to be dealing with perfect strings and perfect pulleys that make the situation a lot easier. All right, so now that we know that, let's go ahead and just go right into our first Atwoods machine problem. So let's say I told you that you had an Atwoods machine such that you had 2 kilograms and 8 kilograms hanging on the pulley. And I asked you, what is the acceleration of the 2 kilogram block? And what is the tension that's in the string? And notice all the way to the left, I've designated my positive direction to be up. So that'll be important to know. All right, so we're going to use the same kind of concepts we learned back in double systems to help us out with this one. Okay, so to find the acceleration, we're going to, once again, treat the whole thing as one system. Now, what makes this problem difficult, or not difficult, but just different compared to what we've seen in the past is, in the past, when you had, let's say, a block attached next to another block, and you were applying a force to the right, both the small block and the big block moved in the same direction. Same thing as if you had like a block attached to another block by a rope, okay, and you pulled this way. That means this block would go to the left, and so would the second block. They would always be going in the same direction. But with an Atwoods machine, we see that that's not the case, because what's happening is the pulley is actually changing the direction. So we need to keep that in mind. So let's think about what's happening here. I'm going to start off by drawing, even though we're going to treat it as one system, and we will, I'm going to start off by drawing a force diagram for each separate block. So for the 2 kilogram block, we have the force of gravity pulling down, and that force of gravity is 20 newtons. I also have the force tension pulling up. And we don't know what that is yet. We're going to solve for that. For the 8 kilogram block, I have its force of gravity pulling down, 80 newtons. And then I have its force tension pulling up. And let's just remind ourselves that, remember, the force tension here and the force tension here are going to be equal. And that's just due to Newton's third law and the fact that we're dealing with the same string. It's just changing its direction. But it's just one string. Okay. Now, you might be tempted, maybe, to think, oh, the 20 newtons and the 80 newtons are going to add together because their vectors are both pointing down, and we've learned that vectors pointing in the same direction add together. And that's understandable, but that's actually not true because if you think about it, the 80 newtons and the 20 newtons are actually opposing each other, and it's because the pulley has changed the direction. So even though they're both facing down, in reality, they're actually fighting against each other. So here's what I tell students to do for these types of Atwoods machine problems. I tell them, pretend that you could take the 2 and the 8 kilogram block system off the pulley. Just take it off the pulley and stretch it out. So what that would look like is this. Here's the 2 kilogram block. Here's the 8 kilogram block. Here's the string that connected them. Okay, and this is where the pulley would have been, would have been draped over it and hung over it, but we've taken it off the pulley. We're stretching it out. Okay, I want you to think about now, if we were to treat this whole thing as one system like we're supposed to, what forces are acting on it? Well, if we stretched it out, the 20 newtons wants to pull this way, and the 80 newtons wants to pull to the right. So think about it. Isn't that pretty much saying the exact same thing as if it was on a pulley? Okay, the 20 newtons wants to pull the system down this way, therefore pulling the 8 kilograms up. But the 80 newtons wants to pull the system down this way, making the 2 kilograms go up. So they're fighting each other. And so when I think about my Newton's second law, and I know Newton's second law is force net equals mass times acceleration. What's the net force that's acting on this system? Well, it's the 80 that wants to go to the right, and it's the 20 that wants to go to the left. So it's 60 newtons as the net force. And that's equal to the mass of the entire system, which is 10 kilograms, times the acceleration, which is what we'll solve for. And so both sides divided by 10, we get an acceleration of 6 meters per second squared. So notice we did the same thing. We still did treating it as one system, but we had to kind of think about it or visualize it a little bit of a different way. Now, the key thing here is that it's asking for what is the acceleration of the 2 kilogram block. And there's a reason why I had to ask that for the 2 kilogram block. I couldn't just say, what's the acceleration like we could before, and that's because the two blocks are going in different directions. So since I'm asking for what's the acceleration of the 2 kilogram block, what does the 2 kilogram block want to do? Does it want to accelerate up or down? And the answer is it wants to go up. It wants to accelerate upwards. Well, have we made up positive or negative? We've made up positive. And that means my answer is a positive 6 meters per second squared. What if I had asked what's the acceleration for not the 2 kilogram block, but the 8 kilogram block? Well, it still would have been 6, but what does the 8 kilogram block do? It accelerates downward, and down is negative. So I'd have to do negative 6 meters per second squared for that one. But that's not what we're doing. We were asked to do for the 2, and so our answer is positive 6. So that's the first part. Now the second part we are going to do just like we've done before, and that is we are going to pick one block, and we are going to solve for the force tension. I'm going to give myself a little more space here. Excuse me, need to stretch it down. There we go. Okay. So, I'm going to choose just one of the blocks. It doesn't matter. I'll choose the 8 kilogram block. So if I draw a force diagram for the 8 kilogram block, I've got force gravity down, and that's equal to 80 newtons. And I've got force tension pulling up, which is equal to a question mark, because that's what I'm going to solve for. So I'm going to use my Newton's second law. Force net equals mass times acceleration. But now I'm just looking at the 8 kilogram block. Okay. So I am now going to solve for what is the tension. Well, and the tension comes from force net. So force net is combined of two forces, force tension plus force gravity. That's equal to the mass times the acceleration. So force tension is what I want to solve for, plus my gravity is 80. But is it a positive 80 or a negative 80? Since I've made up the positive direction and gravity is pointing down, it's a negative 80. That's equal to the mass, which is 8 kilograms, times the acceleration. Now we've said the acceleration is 6, but since I'm doing it for the 8 kilogram block, is that a positive 6 or a negative 6? And the answer is it's a negative 6. Okay, so now all you have to do is just clean it up and solve for force tension. So 8 times negative 6 is negative 48. And I get force tension minus 80 on this side. I'm going to add 80 to both sides. And negative 48 plus 80 is going to give me my force tension of 32 newtons. And a good way that you can check to make sure that you're right on these types of Atwoods problems is that the force tension that you get should be between the two values that you get for gravity. So for example, my two gravities were 20 and 80, and so my tension force should be in between there, which 32 is, so I know that I most likely probably did it right. Okay, let's do another one. All right, same situation here. 3 kilograms and 11 kilograms. What's the acceleration of the 11 kilogram block? What is the tension in the string? Okay, so once again, I'm going to draw my force diagrams for the blocks. I've got, on this one, force gravity is 30 newtons. Force tension is pulling up. On this one, I've got 110 newtons of gravity, and then force tension is going up. These two force tensions are the same. Now, I'm going to imagine that I'm taking it off the pulley system and stretching it out. Okay, and then if I were to treat that as one system, what I end up getting is end up getting a force of 110 newtons pulling this way, and a force of 30 newtons pulling this way. So my force net equals mass times acceleration. My net force is going to be 110 minus 30, or 80 newtons. That's equal to the mass of the whole system, which is 14 kilograms, times my acceleration. 80 divided by 14 will give me an acceleration of 5.71 meters per second squared. But notice it's asking for what's the acceleration of the 11 kilogram block. The 11 kilogram block is going to accelerate down, and down is negative. So that I actually need to have a negative 5.71 meters per second squared. All right, that was solving the first question, which was what is the acceleration. Second question is what's the tension. Remember, when we look at the tensions, we're going to just pick one of the blocks. Doesn't matter which one. I'm going to go ahead and pick the 11, since that's what the problem's asking me to do it for. But it's the same, doesn't matter. So the 11 kilogram block has its gravity of 110 newtons pulling down. Force tension's pulling up. That's all there is to it, so I'm going to plug that into force net equals mass times acceleration. Force net's going to come from force tension plus force gravity. Plugging in numbers, my force tension is what I'm solving for, plus my gravity, well, my gravity is negative 110 since it's pointing down. That's equal to the mass, which is 11 kilograms, times my acceleration. The block is accelerating downward, so it's a negative 5.71 meters per second squared. If we simplify that up a little bit, let's see, let me do that off to the side there. 11 times negative 5.71 is going to give us negative 62.81. And then on the the left side, I just get force tension plus a negative, just makes it minus 110. So I just add 110 to both sides, and I end up getting my force tension is approximately 47.19 newtons. And I do a quick check. It's 47.19 in between 30 and 110, and it is. So I know that I did that correctly. All right, I'm going to give you one last problem here. Go ahead and pause the video and work it out, and then hit play when you want the answer. Okay, let's go ahead and compare the answers. Notice at the very top I've got my drawing as if we took the Atwoods machine off the pulley. And so I've got 30 newtons pulling to the left. I've got 50 newtons pulling to the right, so that would be a net force of 20 newtons, equal to the total mass, which is 8 kilograms. To find my acceleration, that would be 2.5 meters per second squared. And then notice the acceleration is negative, since the problem is asking for the acceleration of the 5 kilogram block. And the 5 kilogram block is accelerating downwards in the negative direction. To find out what my force tension is, I chose the 5 kilogram block again. So notice the force diagram there has 50 newtons pointing down. Tension is pulling up. My net force is going to come from two forces, force tension and force gravity. Tension is what I'm solving for. The gravity is 50, but it's negative 50 since the gravity is pointing down. That's equal to the mass of the 5 kilogram block times its acceleration, which is the negative 2.5. And solving for tension is 37.5 newtons, which I know it's correct because it's in between 30 and 50. This concludes part 1 of the Atwoods machine series.